Hello again. This is my bonus video going over the exact definition of the limit, the mathematical definition of the limit. The definition of the limit is often called delta-epsilon definition of limit because it's going to be a mathematical explanation using the variables delta and epsilon. Let's just jump right in. So let f of x be defined for all x not equal to a in an open interval around a. So that means that your function has to be defined left of a and right of a, but not necessarily at a. That's all of that saying. And then let L be a real number. Then we define the limit as x approaches a of f of x equals L. So this is true if for every epsilon greater than 0, there exists some delta greater than 0, such that if, the way I like to read this is x is within plus or minus delta of a, then f of x is within plus or minus epsilon of L. Because that's what these inequalities basically amount to. So here is a diagram trying to explain what this all means. So if someone, because this equation is for every epsilon, so if someone gives you a random epsilon, then what you want to do is you want to look at L plus or minus the epsilon, and then you have to come up with a value of delta such that whenever a function is within x equals a plus or minus the delta, so a minus delta to a plus delta. So that would be this region from here to here, that for all x's that are in this region, then our function, the y coordinates have to be within plus or minus epsilon of L. Now notice that that region is just from here to here, and that there is a part up here that's also within the region of plus or minus epsilon of L. But the requirement just says that whenever this is true, that whenever you're within plus or minus delta of a, so that's just this part of the equation, that the y coordinates must be within here to here. And that would be true because it's inside of that region. It doesn't necessarily have to go all the way up to the top of that region. Okay? So this is just a drawing sort of explaining how things are working. Now the trick is that you've got to prove that this statement is true for every epsilon. So if epsilon gets smaller, we wouldn't be able to use this same value of delta because this would stick out of the region where the y coordinates are between L minus epsilon and L plus epsilon. So we'd have to decrease delta as epsilon is decreasing. So that's the delta epsilon definition of a limit. You can sort of paraphrase all this by saying that your function has to get arbitrarily close to y equals L. By arbitrarily close, I mean, epsilon could be really, really small. So no matter how close you want, we should always be able to find a region, around A, such that our function is now as close as you want in the y coordinates to L. So trying to use this definition to prove a limit is a little bit challenging, depending upon the limit that you're trying to prove. The simplest limit would be if this limit was, say, the limit as x approaches 2 of 3x plus 7. That one would be pretty simple to prove, but even that, sometimes students who are unfamiliar with proofs are going to have trouble constructing the proof. And that's why this is usually not taught for most calculus courses. Maybe like an honor section, or if you're taking, or if your teacher just really wanted to make sure that you understood the definition of a limit. But really, like I said, in most classrooms, They may just mention this, but usually not test you over it. Anyway, just to show you how challenging these types of proofs can be, let me give you one proof, and this is going to be a proof involving a square root, and show you exactly how that would go. Okay. So I am going to prove that the limit as x approaches 4 of square root x is 2. Okay, so let epsilon be some number greater than 0. Because remember, in the proof, we're trying to prove that for any epsilon, blah, blah, blah. So you have to pretend that someone could choose any epsilon. So that's what this is doing. So let epsilon be any real number greater than 0. Okay. And what we're trying to now prove, let me just state what I'm about to try to prove, is that if square root of x minus 2, oops, start that over. Okay, so this is what we're trying to prove, that if absolute value of x minus 4 is less than delta, then absolute value of square root of x minus 2 will be less than our epsilon. We've got to figure out a sort of a function to put here for delta x that will make this statement true. Okay. Let me show you one sort of attempt at this and one problem that we're going to run into, and then what we can do to fix it. So let's start off with the expression absolute value of x minus 4 is less than delta. I'm trying to sort of manipulate this to become this expression, square root of x minus 2. Now, absolute value of x minus 4, well, x minus 4 you could write as square root of x minus 2 times square root of x plus 2. You know, so if this first statement is true, then this statement is true. Okay. And I'm trying to get this pattern, square root of x minus 2. So I want to get rid of this square root of x plus 2. Well, you know, I can't just, well, let me just do it and explain what's wrong with this. So if I just divide it by absolute value square root of x plus 2 on both sides, I'd have this. You know, so why couldn't I just like let this be equal to epsilon and then solve for delta and call it a day? Well, because then I would end up getting that delta would be this expression. But my delta needs to only be a function of epsilon. It can't also have this variable x in it. So that's the problem. Okay. So what are we going to do so this is no longer a problem? Okay. So we have to take a small little detour. I'm going to put a limit on how big my deltas can be. Like, let's assume that my deltas are going to be less than or equal to 3, and then I'll explain what that's going to do for us, and eventually we'll be able to come up with our equation for delta that we need. Okay, so if you take the expression absolute value of x minus 4 is less than delta, then that means that x minus 4 is between minus delta and plus delta. And therefore, x is between 4 minus delta and 4 plus delta. Okay. And then with this restriction that I put this limit on delta where it can get no bigger than 3. So if delta is 3 or less, okay, that means that this is no bigger than 7, and this is no smaller than 1, so that x is always between 1 and 7. Okay. So now if you think of the expression and factor it like we did before into square root of x minus 2 times square root of x plus 2, we'd have that. Now, since x is between 1 and 7, that means that this, if you plug in 1, you get 3. And if you plug in 7, you get square root of 7 plus 2. So it is, this part of the expression is no smaller than 3 and no bigger than square root of 7 plus 2. Now, I want to use the 1 part of it so that if you replace this with 1, that's smaller than that. Therefore, this expression is less than this expression, which is less than delta. Now, getting rid of the middle, we have absolute value of square root of x minus 2 times 3 must therefore be less than delta. Therefore, absolute value of square root of x minus 2 is less than delta over 3. Then if you connect these two things together, we want this equation to be less than epsilon, so we can just require that this be true, therefore, or equal to. Therefore, we need for delta to be less than or equal to 3 times epsilon. Okay, but remember earlier, we wanted delta to be less than 3. Now we have a second condition that we want to be true. It's for delta to be less than 3 times epsilon. Well, we just want both of those to be true at the same time. So if we want for delta to be less than 2 different things, then we want it to be less than the minimum. So if we just set delta equal to the minimum of 3 and 3 times epsilon, that will make both of these two things true, and then that will complete the proof. Okay. So as you see, sometimes these proofs can give you some strange results. I knew that a problem involving a square root would involve a delta like this, where you have to do a minimum between some sort of arbitrary upper bound that you place on it. I chose 3 just to make the math work out a little bit nicer, so that this was a nice integer 3 as well. Some other limits using the definition of the limit are a lot simpler to prove. Like I said, a linear function is very simple. I think even x squared is not too bad. It's just square root of x is annoying. Anyway, I think that's going to be it for today. Like I said, it's just a bonus video. Don't worry too much on it if you didn't understand everything. Next, we'll be covering the derivative. So have a good day. Take care.